Welcome to this topic, magnetism. So the way this topic is going to be discussed is we're going to start with a simple phenomenon of magnetism, which are going to be discussed in this video. Then after this, we're going to take a look at electromagnetic effects. Then when we get done with electromagnetic effects, we're going to take a look at AC generators. So from the knowledge we're going to acquire about electromagnetic effect, we're going to start AC generators. Then we'll end up with transformers. Let's get started. So we're going to start with properties of magnetism. We all know what magnets are, which are just some material that are able to attract some certain materials also. So the first property of magnetism is the end of a magnet is called a pole. So this is one fact about magnets. Each of the ends of the magnets are called poles. If a light magnet hangs on a string, one end points towards the north. This end is called the north pole. So the earth has got the north pole and the south pole. Okay, so when you just get a string, you tie a magnet, then you let it hang freely, then one end is going to point towards the north pole. All right, that end is called the north pole. The other end points towards the south and it's called the south pole. So materials that are attracted by magnets are called magnetic materials, while materials that cannot be attracted are called non-magnetic materials. For example, we know that magnets can attract some coins. So coins are magnetic materials because they are attracted by magnets. So generally, this is how we can draw a magnet. It has this south pole and this north pole. So when you tie it, when you tie a string here and you let this hang, this is going to point towards the north pole, which is, of course, if you're in Zambia, it will point where maybe UK is, and south where South Africa is. So we're going to take a look at two laws of magnetism. The first law states like poles repel. Remember the laws of charge, where we said like charges repel and like charges attract. The same law applies here, but here we are not talking about charges, we're talking about poles, ends of magnets. So like poles repel, that's the first law. The second law is like poles attract. So let's say we have this magnet which has north and south, and another magnet which has south and north. So if you see these ends, they are the same. If they're the same, these magnets cannot be connected. You can try as much as you can trying to bring them into contact. It might be difficult. These two ends are trying to push each other away. That's what like poles repel mean. But if you get a magnet and another one, then we have got two unlike poles near each other. They're going to attract each other. So just like induced charge, there's also induced magnetism, where magnetism is induced into another magnet, another material. So induced magnetism is just when a magnetic material is turned into a magnet just by being in contact with a magnet. So let's say we have this magnet here, then we get a steel nail. So this steel nail, we put it close to the magnet. What's going to happen is this steel nail is going to be turned into a magnet also. But the way the poles are going to be distributed here is this part which is in contact with the north pole is going to be the south pole, because if it is the north pole, it means repulsion. So it's going to be a south pole so that the attraction is there. Then the other end which is not close to the magnet is going to be the north pole. So this end which is in contact is going to be the south pole, then the other end is going to be the north pole. So we're going to take a look at two magnetic materials, iron and steel, then we compare their properties. So here we have various criteria we're going to look at. Then here we have iron, here we have steel. So this is for iron, this is for steel. So when you talk about magnetization, iron magnetizes easily and strongly, So to magnetize is to turn into a magnet. So when you get iron, you put it into contact with a magnet, it's going to be magnetized, it's going to turn into a magnet easily and strongly. Well, still, it doesn't magnetize easily, and the kind of magnet that's going to be formed is going to be weak. So what about demagnetization? So for demagnetization, iron again is easy, well, still it's hard. Then the uses of iron, it is used to make what are called electromagnets. We are going to study electromagnets soon. Then still is used to make permanent magnets. So the main difference between electromagnets and permanent magnets is permanent magnets are permanent, as the word suggests, while electromagnets are temporal. So examples of applications where we use electromagnets, we have transformers and electric bell. We're going to start the transformer soon. There's also electric bell. Then for steel, we have what are called DC motors and DC generators. We're also going to start generators soon. So they have got special names. Iron is called a soft magnetic material, while steel is called a hard magnetic material. So now we look at magnetization. So like I said, to magnetize is just the process of making a magnet. So there are various methods that can be used to make a magnet. So the first is stroking method. So a stroking method, what you do is, if you have a piece of material that you want to turn into a magnet, you just have to put it like this, then you get a magnet to start stroking the magnet against the material. So you get your magnet to be like rubbing it on the surface of this material. When you reach this end, you go back like so. So you'll be moving just like this. Make sure that you use the same pole. So what's going to happen is the end where you are, where the contact is leaving the material, is going to become the south pole. Then where you are starting is going to become a north pole. This is called stroking method. Then the second method is the electrical method. So if a hard magnetic material is placed into a solenoid, a hard magnetic material is magnetized. The question is, what is a solenoid? So a solenoid is just a coiled wire. You get a piece of wire or engishi, then you make a coil, then you have a solenoid. So for example, this coil here is a solenoid. Okay, so this same coil is connected to a battery, of course, to power to power this. So this is this is called the core. So this core is the material you want to make into a magnet. Okay, a hard magnetic material. Then this is what I've said, the solenoid. So when you connect power, when you power it, not when you connect power, when you power this circuit, as the current flows through the solenoid, this core is going to turn into a magnet. Such a magnet that is formed by this process is called an electromagnet. So now there is a job which is quite interesting. Remember, when we were doing stroking, we discussed how to identify south pole and north pole. What about electromagnetic method? How do you identify the south pole and north pole? So we're going to use what is called Fleming's right hand rule or right hand grip rule. So the right hand grip rule identifies what the north pole and the south pole is by the direction of the current. So let's say we have this solenoid and we have these wires connected. So if the current is moving like this, it goes, it comes up, it goes, it comes up, it goes, it comes up, just like this. If you want to tell which one is north pole and south pole, let's assume we don't know this is north and this is south. What you do is you curl your the fingers of your right hand, like the way they have been done here, with the thumb pointed like this. Okay, the direction the thumb is pointing is where north pole is. Okay, so if the situation was the current moving like this, okay, if the current was moving from bottom to, from top to bottom, so what you could do is you could turn this hand upside down so that now the current can be moving up to down. This is going to point this direction, so your north is going to be here and the other side definitely becomes the south. So that is how to use Fleming's right hand rule or right hand grip rule. Another simple technique is this here. So north is identified if the current is moving like this. It goes, then it comes up. It goes, it comes up. Then south, the opposite. If you want, you can just master one direction and the opposite. You can master one direction, like if current is moving from bottom to up. Actually, current will always be moving from bottom to up. So this, which I'm using, bottom to up, might be confusing, but actually, it's not. I thought it was confusing. It's not, because here current is moving bottom to up, but the opposite situation, when it's opposite, current will be moving like this. So here on the front, you'll be able to see that current is going down. Okay, so because current will be coming like here, down, then it goes behind, then down, behind, down. So if these fingers should point downwards, then this is going to point to the right, and that's going to be the north. Next, we look at demagnetization. So demagnetization is just to make a magnet, to lose its magnetism. So there are some of the processes in which you can demagnetize a magnet is by heating. If you strongly heat a magnet, it's going to lose its magnetism. Next, you can use hammering. If you continuously hammer a magnet, it's going to lose its magnetism. The third and most delicate method is using alternate current and the solenoid. So alternate current is, there are two types of current. There's what is called direct current and alternate current. Direct current is the type of current we get from, for example, batteries. Alternate current is the one that comes from Zesco. I won't go into details. For now, I'll leave it here. So if you use alternate current and the solenoid, you can demagnetize a magnet. So what you do is, a magnet, you place it inside the solenoid, which has an AC supply. Then the magnet is withdrawn away from the solenoid. So you have this solenoid. So this symbol here shows that here there is AC, the supply is AC. So as the AC is passing here, which is power from Zesco is passing here, then you can just withdraw the magnet. You keep on doing this many times. This magnet is going to lose its magnetism. Next, we're going to take a look at quick facts about electromagnets. So iron is commonly used as the core of electromagnets because it is easy to magnetize and also demagnetize. Since electromagnets, they're all about control. You want to magnetize something when power passes, and also to demagnetize it when when there's no power. So iron is used because it magnetizes easy and fast, and demagnetizes easy and fast. Then the strength of magnetism depends on, remember, electromagnets are only magnets when you power them. So the strength of magnetism depends on, 1, the amount of current. They are the current, they are the magnetism. 2, the number of turns per unit length of the solenoid. They are the number of turns, the greater the magnetism. 3, the material of the core. So there are some materials which are bad and some materials which are good. Last, we look at magnetic fields. So a magnetic field is defined as the region around a magnet where magnetic effect can be detected. When you put a magnet and you get, let's say, a coin, wherever such that when you put a coin, you feel like the coin is attracted or repelled to or away from the magnet, those are magnetic fields. So there is a technique on how to draw the magnetic field. What you do, you have to get a magnet and a plain paper. You put a magnet on a plain paper, then use a compass. The compass that is used actually is called a potted compass, but it's okay for now to say compass. So the thing about the compass is it always points where the South Pole is. So get a magnet, you put your compass on the North Pole. So the point of the compass will point somewhere where it thinks the South Pole is. So what you do is you get a pen, you mark where it is pointing. Then you place the compass where you had put a point or where it was pointing, like this. So first you draw where it is pointing, then again you place it here. So at first I drew here, that's where it's pointing. I started from here, then I drew here where it is pointing. Then again I put it, it's pointing here, so I put a point. Again I'm going to put it here like this. Then again it's pointing here. So when you do that, you are going to continue till you reach the South Pole. So when you connect the points, then you have a line of magnetic field. So if you do this, like starting at different points, again, you can take the compass and start here. Again, to point somewhere, keep on doing this, you are going to have a magnetic field. So magnetic field are usually symmetrical, like they can be here and also they will be this side. So at the end of the day, you might end up having something like this. So concentrate on this. So when you're done, you're going to have something like this. So this is a magnetic field. So on the bottom, to end the topic, we're just going to discuss how the field lines, these are called field lines, appear when various poles are brought together. So when you have north and north, actually the way from here, you have seen that we started from north going to south. So the field acts as if they move from north to south. So when you have north, north, the fields are going to be coming out. So because of this, they are all coming out. When you're trying to push them, the fields won't, there's no link here. The only way they can attract is if the field are able to move from north to south. But because this is north and this is north, so they are going to be getting away trying to find south. That's why they cannot attract. Then if it's south and if it's south, the same is going to happen. South is where the magnetic lines, the field lines come. So when you try to push the south together, they cannot attract because these are only looking for, or they can only come from the north. Since this is south, they all want to get inside south. Then third is way of north and south. So in this case, north, they want to go to south here, but there's south here. So they can just skip and go to this one, which is near. That's why they attract. So this marks the end of magnetism part 1. Hope you have enjoyed.